Alright guys, another video for you here. This is a video that I'm piggybacking a previous video on the build, or basically the walk around technical description of this my mountain cycle San Andreas that I modified for electric drive. This video specifically is regarding the use of radio control based equipment in a bicycle application. Most bicycles, electric bikes I should say, have a hub motor mounted at the rear. Hub motors, they're easy to install and generally reasonably priced. They definitely have their place, but there are issues with them. Hanging a lot of weight, rotating in a wheel is very unsatisfactory from a handling standpoint, and the power suffers typically unless you're running an enormous motor, which compounds the weight issue. So it's generally best to get any heavy components, power-related equipment to the middle of the frame, and then drive the rear wheel with a separate either chain or belt drive. And most mid-drive systems that have a motor mounted in the center of the frame would drive the cranks, and normally you'd have a freewheeling crank set, so the drive unit would drive the crank sprocket and therefore drive the rear wheel. There are power limitations there. There's benefits to that, such as having multiple gear ratios available, but when you're running higher power you don't need multiple ratios, and but running high power you end up with a large motor, and there's just issues. So about 10 years back I found that you can use motors and controllers that were designed for the radio control industry that are very small and very, very power dense, and apply them to a bicycle application. There are certain problems to doing that. One of the main issues is motor RPM. In an electric bike application, most motors would run at anywhere from 1 to maybe 3,000 RPM at the high end. RC motors start at 3,000 or 4,000 RPM and go up to 13,000 or 14,000 RPM or even higher. So that requires a very deep reduction. Now, the way I get around that is by running a deep reduction ratio, small motor pulley to a large secondary pulley to drop the ratio down. This happens to be 7:1. And then from there, a very small freewheel that drives the chain to a relatively large rear sprocket at the wheel. That drops the very high motor RPM, in this case 13,000 RPM from the motor, down to a reasonable RPM at the wheel. In this case, the bike runs 28 miles per hour at full throttle with this gear ratio. So that's the way I get around the RPM issue. Now, the other issue is that in most electric bike applications, you've got a censored motor, well, either a brushed motor or a brushless motor that has Hall sensors within the motor. Those Hall sensors would tell the motor controller what position the rotor is within the motor can in order to gain proper timing between the controller and the motor. In a radio control application, the vast majority of equipment used in radio control, the motor and controller would be sensorless. That means that they don't use position sensors to sense the position of the rotor. They use a back feed, what's called a back EMF signal from the motor, as it in between winding pulses, it sends a back feed signal to the controller to gain synchronization between the two. There's benefits to this system. It's more efficient. There are certain startup 0 RPM concerns with the sensorless system, but certain controllers get around that, and the type of controller that I use can deal with the startup issue without a problem. Now, this motor is an Astroflight 3210. They also make a 3215 motor, which is longer, and a 3220 that's even longer. I prefer the 3220. In this case, I'm using a 3210 motor, a 5-turn 3210 motor, just to save weight, though admittedly I'm going to go to a larger motor shortly, or go back to a larger motor, which is where I had started. So that's the motor. The controller This is a Castle Creations, you can see Edge 160 controller. This controller is a sensorless controller designed for large-scale radio control airplanes, and the controller takes the power from the battery. I have no on-off switch. I just merely plug the battery directly into the controller. On this bike, this is sort of a research bike. I just have some wires zip tied. I like to add components and remove them for testing purposes, so in this case it's best not to have an ignition switch. I just plug right in. So it's a 12-cell lithium polymer battery that is 50 volts hot off the charger. That power runs into the controller. As I pointed out before, the controller runs the motor. Now, sounds very simple, except for one thing, and that is that the signal wire going to the controller to give you throttle control, that signal wire, in an e-bike application, you have your twist grip throttle, and that plugs right into the controller. In a radio control application, you normally would have the controller, this connector here, would plug into the radio control receiver, and that receiver sends a pulsed signal, not a resistive signal, to the controller. At zero throttle position, you'd have a 1 millisecond pulse, and at full throttle, you have 2 millisecond pulse. So the controller looks for a 1 to 2 millisecond pulse sweep to give it throttle. This is a very interesting situation. The solution I've come up with is inside this black box here, and inside this box I have a small circuit board that you can obtain out of a Servo Tester, or there's a number of electronics applications for a small circuit board that outputs a varying pulse. I use a Servo Tester made by Astroflight, the motor manufacturer, and I modify it. So inside this box, again, is that Servo Tester board that outputs a pulsed signal into the receiver. This is an endpoint adjustment. I can set that to tell the that circuit board how much throttle I want. So if I have it set at the midpoint, that would, at full throttle, would give me 50% throttle at the controller. So it's a nice fine-tuning adjustment. So inside this box, you've got that pulse generating board and a voltage regulator to take the 50 volts from the battery and drop it down to 6 volts that Servo Tester pulse board can accept. So it gets a little complicated. So you've got the throttle with this, which is this signal lead here, going into my PWM, or pulse width modulation interface box. That converts the signal to a pulsed signal so that the radio control receiver, or excuse me, radio control controller can properly control the motor by way of the twist throttle. So it gets a little bit confusing. So again, the flow would be a voltage from the battery into the controller to the motor. The speed of the motor is controlled again by the twist grip throttle. This is a Magura throttle in this case, through the sensing wire to the PWM box that converts the resistive signal from the throttle to a pulsed signal that the controller can interpret, and that controls the speed of the motor. So it's a little bit complicated, but it works very well. The controllers are about 20% the size of an electric bike controller and about 5 times more powerful. Very, very efficient. They run nice and cool. The motors are about 4 times more powerful per pound and per cubic inch of size than a typical e-bike motor would be. The radio control lithium polymer batteries are more powerful than typical electric bike batteries. So there are definitely benefits to a system like this, but it requires a lot of mechanical ingenuity to get it to work, and some electrical know-how to get it all set up. And admittedly, radio control equipment is about 3 or 4 times more costly than typical electric bike componentry. So building a bike like this, and I do a full walk around of this bike on another video, you can look for that, but completely building a bike like this from scratch is going to cost upwards of probably $6,000 or $7,000, and the electric drive portion of that would be about $3,000, plus all the custom work and all the bicycle components. So it's not cheap, but setting a bike up like this, it's similar to purchasing a Ferrari. Just the quality is very, very high performance, very lightweight, good handling, and again, there's applications for every type of system though. A typical e-bike system, drive system works great for most applications, but when you really want to take it to the ultimate edge, there's really nothing quite like the RC systems. They're super light, super small and compact, super powerful, and very efficient. This particular bike is about between 18 and 20 watt-hours per mile at 25 miles per hour, which is among the most efficient electric bikes you could ever purchase or build. So, and yet the power density is very high. So you do get what you pay for. Anyway, be sure to look for the walk-around video of this bike. I give a more in-depth description of the technical aspects of the bike. And thank you.